Let's start with a simple problem. For each element ai of an array, you need to find out the next smaller element. Some of you might already know that this is a classical problem which can be solved using monotonic stack. But if I were to ask you to implement the solution right now within 5 minutes, will you be able to code up the solution without any bugs? If your answer is yes, let me make the problem a bit more difficult for you. Instead of finding out the next smaller element, can you find out the second next smaller element? Do you think the monotonic stack can be modified to answer this query as well? And if you think so, do you know the modifications that are needed to make it work? Probably not. So, in this video, I'll share a trick with you using which you can answer both of these queries using a very simple code that you can implement even in your sleep. Along the way, we will also talk about contribution technique and its two variations that you can use to solve Codeforces problems. After learning these techniques, you will see that we will be able to solve a 1900 and a 2400 Codeforces rated problem with ease. I have added the easy version of these problems on my Codeforces group as well, the link of which you can find in the pinned YouTube comments. By the way, to answer the question that we asked previously, the answer is yes, the monotonic stacks can indeed be modified to answer this query, but that is not something that is easy to come up with yourself. But in case you are interested in how monotonic stacks work to answer this first query, you can take a look at this video on my YouTube channel that talks about the monotonic stack idea. The name of the video is Optimizing DP with Monotonic Stacks. How do you find out the next smaller element for an index I? One simple approach to do that is to iterate over this entire array from left to right, and every time you encounter an element that is smaller than ai, you color it as red and you say that this particular element is alive, and all the elements that are not colored, they are dead. Once you have marked all the valid elements in red, to find out the next smaller element, you can start at the index I and keep going right till you hit the first alive element or the first red colored element. That would be the next smaller element. The time complexity of this approach is O of n plus n. The first n is for marking all the valid elements in red, and the second n is for traversing from here to the first red element. If you want to optimize it, one thing that you could do is, once you have colored all these elements in red, you take their indices and insert all these indices, all the red indices in a set. Once you have inserted all the red indices in a set, and let's call that set as the alive set. So to find out the next smaller element, you can simply search for the upper bound of the index I in that alive set, because that will point you to the first red element that is to the right of the green element. So the time complexity of that approach is O of n plus log n. So overall it is still O of n. To optimize it even further, you can notice that instead of iterating I from 1 to n, you can traverse I from small element, the smallest element, to the largest element. That is, you go from small to large. If you do that, you will not need to create a new set every time for each ai, because by the time you are investigating this particular element, all these smaller elements than this, for example this and this, they have already been processed and they are present in the alive set. Now one observation you can notice is that as soon as an element goes into the alive set, it will never die. Why? Because you are processing elements from small to large. So every element AI that you process, it will need to mark all the smaller elements before it in red. Therefore, once an element is inside the alive set, it will never die. So if you process these elements in their sorted order, that is from small to large, you can see that for each element AI that you are currently processing, to find out the next smaller element, you just need to look into the alive set and query for the upper bound. To find out the previous smaller element, you query for the upper bound and then you go one step back. To find out the next smaller element, you query for the upper bound and then you go one step forward. To find out the second previous smaller element, you query for the upper bound and then you go two step back. So this is a simple approach that solves the problem in O of log n per index. So overall time complexity is O of n into log n. So just to summarize the idea, you iterate over all the elements not from left to right but in their sorted order from small to large. And every time you encounter an element, all the smaller elements than it, they are already in the alive set and they are colored as red. So to find out the next smaller element of the element that you are currently processing, all you have to do is look into the alive set and query for the upper bound. And then if you move one step forward in the alive set, you will get the next smaller element. So using this technique, you can answer not only the second NSE but the third NSE as well. So all these queries can be answered efficiently using just this simple idea of iterating over the elements in their sorted order and then keeping an alive set that indicates the red bars, that is all the elements that are smaller than the currently processed elements. Then you just keep on querying upper bound in that set. Now that we know how to compute the next smaller element as well as the previous smaller element, let us solve a 1900 rated problem from AtCoder Grand Contest. You are given an array containing distinct integers and you need to find out the sum of minimum value of all subarrays that exist. Instead of iterating over all the subarrays, then finding out the minimum and then summing it up, we will utilize something known as the contribution technique. We ask the question, how many subarrays exist in which the ith element is the minimum element? So we know that it is easy to find out the next smaller element and the previous smaller element. So we find them out and we color it as red. And we suppose that R is the index of the next smaller element and L is the index of the previous smaller element. Now, if ith element is the minimum element, definitely it needs to be part of the subarray. But where can the subarray begin? Can it begin at this bar? No, because if this was the part of the subarray, then the minimum element would be this red bar and not this green bar. So in fact this red bar is like a danger zone. That is, if you cross this red bar or if you even touch this red bar, this green bar cannot be a minimum anymore. So the subarray that we are looking for definitely needs to start in this area. And we know that in this area all the elements are definitely greater than this. Why? Because this is the first smaller element to the left. So it can be this bar, this bar, this bar, or even this bar, because I comma I is also a valid subarray. So how many valid indices are there for the starting endpoint of the array? So that would be I minus L. That is, you can include I but you cannot include L. That is why it is colored red. So if you call A as I minus L, similarly, where can this subarray end? It definitely cannot end here, because if you cross this danger zone, the minimum would become this. So this will no longer be the minimum. But if you are anywhere in between, the minimum would be still a of I. So if you call b as r minus I, then you will see that there is exactly a into b sub arrays in which the ith element is the minimum element. So the contribution of the ith element is nothing but a into b into a of I. And then you sum it up for all indices that exist. So to find out these elements, these red elements, we have already discussed that you need to process these elements in small to large order, so that by the time you are at a green bar, you already know the location of this and this red bar. This is the code for this problem. To iterate over the elements in small to large order, you can store them in a set clubbed with their indices. Then you iterate them in small to large order, and to query the next smaller element, you simply query the upper bound that would indicate the next smaller element. And to query the previous smaller element, you query the upper bound and then you go one step back. And once you have processed the current element, you mark it as alive. This way you can find the PSC as well as the NSC. And as we discussed earlier, the contribution of the ith element is nothing but a into b, where a is the number of elements in between the danger zone and b is the number of elements in between the danger zone to the right. So that is why ai into a into b. That was easy. Now let's solve a 2400 rated problem that asks you to compute the same thing, but this time in the ith query you need to delete the ith element from the array and then compute this expression. You might try to apply the contribution technique again by thinking about what happens to the value of the expression when you delete the ith element. But if you notice that if you delete the ith element, the next minimum is not really predictable, because you already counted all these subarrays in this range. But once this ith element is gone, the next minimum is very unpredictable. It could be this element, this element, this element, this element. There is no pattern to it. So that is why this contribution technique approach is a dead end. So what we can instead do is another variation of contribution technique, wherein the element that you are currently looking at, you do not delete this element. Why? So that you can propagate the contribution of this element to the other elements. So we will say that we will keep the ith element alive, and then we will think about what is the contribution of the ith element to the value of f of 1 or f of 2 or f of 3, etc., when this particular element is deleted, or this particular element is deleted, or this particular element is deleted. So once you keep the ith element alive, then the new minimum becomes predictable. But if you start deleting the ith element, it becomes very unpredictable. So this is another variation of contribution technique, wherein you do not remove the element that you are currently investigating to make things easy for you. So that is why for each j not equal to I, we will ask what is the contribution of the ith element when the jth element is deleted. Now you will notice that this green bar and these red bars, they partition the graph into 4 disjoint segments. So there are 4 regions, and keep in mind that all the elements in a region are uncolored. So this is region 1 with 3 elements, this is region 2 with 3 elements, this is region 3, and this is region 4. So now we will talk about what happens when an element is deleted in any of these regions. How does the contribution of the ith element changes? But apart from these 4 regions that you see, there are also 2 partition points. So this is the L partition point for the red bar and the second partition point. So we will also talk about what will happen when you delete this red bar, what will happen when you delete this red bar, or what will happen when you delete any element in this particular region. What happens when an element from region 1 is deleted? Let us select an element randomly from region 1 and delete it. So this element is colored as gray, indicating that this is no longer in the array. Now the array contains n-1 element, and how do we compute the f value of this particular reduced array? What is the contribution of the ith element to the f value in this array? You will notice that the contribution doesn't really change because there were a choices to select the left endpoint, and these choices still exist. So these were the choices, they still exist. And there were r choices, there were b choices to select the right endpoint, and these choices still exist. So there will be exactly a into b subarrays still, in which ith element is the minimum. So the contribution of the ith element when this element is deleted is still a into b into a of I. So we can iterate over each of the element in region 1 step by step, and then add a into b into a of I to each of their f value. The time complexity to do that would be O of n, because there can be at most n elements in region 1, but that is fine. We are looking for a correct solution, not an optimal solution. What happens when an element from region 4 is deleted? If you randomly select this element and delete it, you will notice that the contribution of the ith element does not change. It is still a into b into a of I. So we can do the same operation for region 4 as well. That is, we iterate over each of the element in region 4 and add a into b into a of I to each of their f value. Now, what happens when an element from region 2 is deleted? Let us randomly select this element and delete it. It is marked gray, that means it is deleted. Now, what is the contribution of this green element in this reduced subarray where this element no longer exists? You will notice that since this element is gone, the number of choices for the left endpoint has reduced from a to a minus 1, because one element is now missing from region 2, but the number of choices for the right endpoint still remains b. So that is why the total number of subarrays in the new smaller array in which this element is the minimum would be equal to a minus 1 into b. So we can iterate over each of the element in region 2 and add a minus 1 into b into a of I to their f value. Similarly, what happens when an element in region 3 is deleted? If you randomly delete this element from region 3, you will see that in the resulting array, the choice for the left endpoint remains the same. It is equal to A. But one choice for the right endpoint is gone. So the total number of subarrays in which this element will now be the minimum would be equal to A into B minus 1. So we will add a into b minus 1 into a of I to each of the f value in region 2. Now, what happens when the partition point is deleted? That is, this element was the red bar previously, and this was the PSC of this green bar. But what happens when this PSC itself is deleted? What will be the contribution of this green bar in this new array of n-1 elements where its PSC no longer exists? To do that, you need to find out how many subarrays in which the green bar will now be the minimum. So on the right hand side, nothing changes. You will see that there are still B choices to select the right endpoint such that this element is the minimum. But on the left hand side, once the PSC is gone, once the previous smaller element is gone, a new opportunity opens up for it to extend for the minimum. So what we are looking for is the second PSC, that is the element that is smaller than this green bar that exists after this element. So without loss of generality, assume that it is this blue bar. So once this element is gone, the choice of the left endpoint is all of these bars. So if you say that the index of the second PSE is LL, then the number of choices to select the left endpoint is I minus LL minus 1. Why is this minus 1 appearing over here? Because one element is missing from the array, that is the element at index L. So now this is the number of choices for the left endpoint and the right endpoint remains the same. So if you call this expression as P, you can say that there will be P into B subarrays in which this green bar would be the minimum. So we will add P into B into A of I to the F value of this. Similarly, what happens when the second partition point is deleted? If this is deleted, and assume that we already know how to compute the second NSE, and assume that this is the second NSE, this blue bar, and we already know how to compute the second NSE using iterator in a set. That is, you find the upper bound and then you go one step forward. So if this element is deleted, then the choice for the left endpoint remains the same, which is equal to A, but the choice for the right endpoint becomes RR minus I minus 1 because one element is missing, and the number of subarrays is product of them because they are independent choices. So if you call this expression as Q, there will be A into Q subarrays in which the green bar will be the minimum in the resulting array after deleting this element. So you add A into Q into A of I to the F value of this. So now we have seen that what will be the contribution of this green bar to any of the element after they are deleted, and that solves the problem. So the O of n is for performing all the operations combined for adding some delta to the prefix. But since there is a set as well, so the overall time complexity for this problem is O of n log n. For the code, first we write a utility function that will iterate over all the elements of a given region and add the contribution to each of the element in that region. Then to process the elements in small to large order, we will store them in a set. Then we start processing the element and then we find out the location of the red bar here and the red bar here. That is as simple as finding the upper bound, and then the upper bound is the next smaller element, and then if you move one step back you will get the previous smaller element. Now that you have the location of L and R, you compute A as I minus L, B as R minus I, and then in region 1 you add A into B into X because this doesn't change. In region 4, which is R plus 1 to N minus 1, you add A into B into X, that also doesn't change. And in region 2 you will add, so region 2 is L plus 1, this is L plus 1, and this is I minus 1. So in region 2 you add A minus 1 into B into X because one element will be missing in the choice. And in region 3 you will add A into B minus 1 into X. Then for the partition point you need to find out this blue bar. So finding out the blue bar is just finding out the finding out the upper bound and then moving one step forward. So that is why RITR plus plus. And finding out this blue bar is finding out the upper bound and then moving two steps back. So we move one step back because we are using the iterator that we had computed earlier. Because we were already at this location, so we move one step back. Then we find out the value of P. So P is the new left choice. So left choice is I minus LL minus 1 because one element is missing. Similarly, Q is RR minus I minus 1 because one element is missing. And then for this partition point, the contribution would be P into B into X, and for this partition point, the contribution would be A into Q into X. So you add it to that. And finally, you print all the F value. So the time complexity of this code is N O of N square log N. Why? Because you are using this function to add something to each element in a range, and this function has the time complexity of O of N. So that is why the overall time complexity is O of N square. But if you want to optimize it, you can notice that this function is nothing but adding a delta to a subarray. And how do you optimize the process of adding a delta to a subarray? you can simply use prefix sums. That is, if you store the prefix sums in instead. So for example, if you do this, right, so whenever you need to add something to a range, you add it here and then you subtract it here, and finally you at the end you sum up all the elements in the array, that will retrieve the final array. So this is a very standard trick of keeping the difference array and then converting it into a prefix sum array, and that will help you solve the problem in O of n. In this video, you saw two variations of contribution technique as well as a foolproof method to compute the next smaller element as well as the second next smaller element. I hope you will no longer be afraid of computing these expressions in case you encounter them in future. I have added the slides, code and some practice problem and some similar videos related to this concept in the pinned YouTube comments, and the code will be available on cfstep.com.